Firstly, we set all of our variables to their set pins. These are all constant integers, as they will never change throughout our function. This will always be connected to 7, echo pin always connects to 8, buzzer will always be connected to 10, and LED will always be connected to 12. Our void setup, we start with serial begin 9600. Then we state our pin modes. Our trig pin is an output, as this sends out the ultrasonic wave. Echo pin is an input, as this detects when the ultrasonic wave comes back. Buzzer is an output and LED is an output. In our void loop, we first use the long function, as this helps us maximize the number of digits that we can use. Then this begins the release of the ultrasonic wave. Our trig pin starts off as low. We use delay in microseconds, which gives us very high accuracy. Then digital write pin high releases the wave. Delay microseconds 10, and then trig pin low ends the trig pin's function. Next we use the pulse in function, which allows us to get the input from our echo pin from when the ultrasonic wave gets detected. Then microseconds to inches and microseconds to centimeters. These two functions will convert our time into a distance. And then over here, this is just for show. This prints out our inches and centimeters so we can see it in the serial monitor. I'm sure you could recognize the pattern here. The further away, up to 15 centimeters, the object is, the less frequent the buzzes and warning flashes are. And then as the danger is closer and closer, it starts to buzz more and more. Over here, we use an if-else-if statement to code for the buzzer and the LED. So at first, we have if our centimeter value, which we get from up here, if our centimeter value is between 10 and 15 centimeters, so this shows how far away the object is. If it's between 10 and 15 centimeters, then the tone of the buzzer will be set to 1000, that's the frequency, and both our buzzer and our LED will be set to high. This then gets delayed for 1 second before being set to low. Then no tone basically turns off the active buzzer. Then we set another delay for 200 milliseconds. And then this whole thing repeats if it stays at 10 centimeters to 15 centimeters. As we move on, we've got another one between 5 centimeters and 10 centimeters. This is an else if statement. Same thing over here, except we've halved the delay for both of these sections from 1200 to 500 and 100. Now, for our final else if, which results in a buzzer beat, we've got else if centimeters less than 5. This is the highest level of danger, as it is the closest where we can get a buzzer beat. So we've got our delay as the shortest. So we've got a very, very high frequency of beeps and flashing lights, where our buzzer is set to high and our LED is set to high. Then after 250 milliseconds, it is set to low and set to low. Then a delay of 50 milliseconds. Now, just so that we don't have the buzzer beating constantly and the LED constantly on, we also have to state that if centimeters is larger than 15, both the buzzer and the LED have to be set to low. Now, as you can see here, these are calculations that were already set there from the example sheet that I'd taken this from. Most of this code I have changed up, so if you want this, I'll probably have it linked down in the description. But other than that, if you go File, Examples, Sensors, and Ping, there is the template, somewhat of a template of how the sensor would work. However, this does not work for the sensor that I'm using, which is the HC-SR04, as it has a different number of pins and you have to code for a different input and an output, whereas the example sheet codes for a sensor that has the same input and output. In terms of components, we've got an ultrasonic distance sensor, an active buzzer, which I've got a little sticker on to distinguish it from the passive buzzer, an LED, which is red, and a 100 ohm resistor. The ultrasonic distance sensor has 4 different male to female cables. They're being connected, as you can see here, to ground, echo, trig, and VCC. Ground, I've got connected to the ground wire, which is connected to this blue line over here. The second one being echo, I've got connected to pin number 8. The third one being trig, I've got connected to pin number 7. And the fourth one being VCC, which I've got connected to the 5-volt pin. This wire connects from pin number 12 to this 100 ohm resistor, which connects to this red LED, which then connects to this gray wire to connect it to the ground, completing the circuit. Here is that in a real world scenario, this buzzer will not always be activated. We would have a certain button, such as a parking button, which allows the system to activate. As if this isn't activated, then we would have many cars next to us on highways activating the system, buzzers beating, LEDs flashing, and this would just not be ideal. Now the last thing I would like to show is the serial monitor, so you could actually see the output. As you can see right now, our centimeter values are very skewed because we've got nothing in front of it right now. So it's just bouncing off of the wall that's far behind me, on my shoulder. Now I'm about to move my hand closer and closer to the sensor so you can see the change in the values. Here, but as soon as it gets 15, the buzzer goes off. Closer and closer and closer and closer. Let me get further away. I've also removed the 100 millisecond delay, which is why these values are coming up super fast, but this helps us with in real life scenarios. In a high danger situation, you don't want to have that. You want it to be instantaneous feedback, prevent crashes. One final thing I would like to say is that the distance values can obviously be changed in the code pretty easily. I've just had them as 15, 10, and 5 so that I could show it to the camera very easily. However, in a real life scenario, obviously there would be much larger values because you don't want it to be pushed so closely.